In section 1.5 we're looking at algebraic division, and it would be something like this. Well, let's start with an example. Let's say we've got 25 divided by 6. Well, we know that that is 4. And we're so sophisticated we could probably even work it out as something more than 4, but let's think about it as 4 remainder of 1. Okay, now we know that 4 and remainder of 1 means that 25 equals 4 times 6 plus 1. Okay, but we also know that 25 divided by 6 equals 4 plus 1 divided by 6. Okay. Now then, when it comes to algebraic fractions, we're going to do the same sort of thing, right? So what is the algebraic fraction equivalent of a top-heavy fraction? Well, the algebraic fraction equivalent of a top-heavy fraction would look like this. Here's the example from the book. Now, we've met this sort of thing before. It's totally familiar. It's a division, isn't it? It's an algebraic fraction division question from whatever chapter it was in the last book. So we can say, well, we can do that, and we can get an answer. And if we did the algebraic fraction division, we'd end up with x plus 7, remainder 22. And we could think of that as being, well, x plus 7, remainder 22. Well, that's the equivalent of this. We could think of it as being this: x squared plus 5x plus 8 equals x plus 7 times x minus 2, and then we've got to add on the remainder of 22. Or we could think of it like this: x squared plus 5x plus 8 divided by x minus 2. So this is so this one here is the equivalent of the second one here. This here, we're going to do it like this. This is the algebraic fraction into mixed numbers sort of version of this. So that would be x plus 7, what am I saying? Oh, I've lost myself a little bit. Okay, so that would be x plus 7, which is our answer. That's the equivalent of our 4, plus 22 over x minus 2. Okay, so if you just look at every time we've got a 25, it's the equivalent of this expression here. Every time we've got a 6, it's this expression here. Every time we've got a 4, it's this expression here. These things algebraically mean the same as these things numerically. Okay, and if you want to double check, you could do that algebraic division with whatever method you used when we did that chapter in the last book, and you should check that's where the x plus 7 comes from. But that's the right answer. And again, I'm just taking these from the book, page 14. Now then, when we do this, then we can do it by a polynomial division. And if you look at example 11, that's exactly what they do. They do a polynomial division, and then we just write the answer out in a different way. Instead of writing it as two things times together plus a remainder, or as an answer with a remainder of, then we get that. Now, the other thing we can do is we can think of this like a partial fraction question, and we can go straight from this division to saying, well, okay, this is a quadratic divided by a linear term. It's going to give us a linear expression. Sorry, a quadratic divided by a linear expression is going to give us a linear expression, and the remainder is going to be a constant, because the remainder sort of has to be smaller than this bit. And how that manifests itself in polynomials is the degree of the thing. So the degree of a polynomial is the highest power on the x. So the highest power on the x here is a 1. So the highest power on the x on the remainder has to be a 0. So in other words, a constant term. Okay. So from dividing by a linear term, the remainder has to be a constant. So let's take the example that they give us here: x cubed plus x squared minus 7 divided by x minus 3. Okay, let's do this example. Well, if I did that, I know that what would I get? I'd get that x cubed plus x squared minus 7 divided by x minus 3 would have to be equal to a cubic divided by a linear term would give us a quadratic, right? So it would be something times x squared plus something times x plus something, and then added to that, there's going to be a constant divided by this linear term, because that's my remainder divided by that bit, okay? So that's like the, that's like 4 plus 1/6, all right? Cubic divided by a linear term is going to give us this quadratic, and then I'm going to have the remainder divided by that. So I can think of it that way around. Now, if I think of it that way around, this is now just a partial fraction in question, right? Okay, these aren't all fractions over here, but if I times everything by x minus 3, I get this quadratic times by x minus 3 plus d, and now I can use equating coefficients methods, or I can use substitution methods, and I can find a, b, c, and d, okay? Let's just have a go at this one. I'll do this all the way through. Feel free to, obviously, to scan through and ignore this if you feel like you can do this from here. X times ax squared is ax cubed. X times bx is bx squared. X times c is cx. Minus 3 times ax squared is minus 3ax squared. Now I'm going to write this here so that I've kind of got the ax squared, the x squared terms together. Minus 3 times bx is minus 3b x, and minus 3 times c is minus 3c, and then I've got d as well. So instead of writing it all on one line, I've written it deliberately sort of staggered so that when I collect the terms together, it makes life easier. I get a lots of x cubed. I get x squared times b minus 3a. I get c minus 3b lots of x, and I get minus 3c plus d. Now I'm going to do this by equating coefficients because it's the method I like. So if we equate coefficients, the coefficients of the x cubed terms give us 1 on this side equals a on this side. Coefficients of the x squared terms give us 1 on this side is b minus 3a on this side. The coefficients of the x terms, well, there's no x term here, so the coefficient is 0, is equal to c minus 3b. And the constant terms, minus 7, is equal to minus 3c plus d. So a equals 1. From this one, if a equals 1, b minus 3 equals 1, so b is equal to 4. C minus 3 lots of 4, so c minus 12 is 0, so c has got to be 12. And minus 3 times 12 is minus 36 plus d, so d is going to have to be, oh dear, my mental arithmetic's failed me, but oh, fortunately I've got a book sitting next to me, 29. Okay, so if I then write this out again up here with those numbers in, I end up with the answer in the book that this thing here was equal to 1 lot of x squared, 4 lots of x, 12, and 29 over x minus 3. Okay, so you can do these as polynomial divisions, and once you've done the polynomial division and found the remainder, you can write it out as a mixed number, or you can do it as a treat it like an algebraic, like a partial fraction question straight away, and realize the answer is going to be, well, cubic divided by linear, quadratic plus constant over the remainder. Okay. Now the next one, example 13, gives us a quartic divided by a quadratic. Well, we've got a quartic divided by a quadratic, two ways forward. One, again, you can do the polynomial division. Your remainder, because this is a quadratic here, your remainder might be a linear term, but that's fine. We can do polynomial division and get a remainder of a linear term, and then we can go from there. We can write it as, in the same way as back here, the top thing divided by the bottom thing equals the answer plus the remainder over the same bottom thing over here. Well, we can do that. Or we can think of this as a quadratic, quartic divided by quadratic is going to give us some quadratic plus something over this. Well, what am I going to have over that? I could have a linear term plus c plus dx plus e over that quadratic. And then if I look at that quadratic, what can I do? Can I factorize that quadratic? Because if I can, I could factorize that quadratic and then partial fraction over here as well. Okay, so sometimes that quadratic will factorize and sometimes it won't. I mean, hopefully you can check that for yourself whether that one factorizes or not. I won't spoil the surprise. You can just double check it. Now, the only other thing to mention here, so we can do that by both of those methods. One, we can write it out like this. Then we can times by the denominator on both sides and equate coefficients, or substitute in this case, 1, 2, 3, 4, 5. So we need 5 different values of x. They can be any values of x you like, and you can substitute them in, and you can solve it that way. The only thing that sometimes confuses people is because in the last book we never did a polynomial division with anything other than a linear term on the bottom. So very quickly, let's just do an example of that. I personally don't like doing these with polynomial division with the bus stop method. I always think it takes more time and takes more effort, but I know that I'm in the minority. A lot of people like it. We're just following exactly the same method as we know, which is first term divided by first term. Now the first term here is no longer an x squared term, an x term, it's an x squared term, but that's fine. X to the power of 4 divided by x squared is x squared. Term that I've written on the top times by all of this is x to the 4, x squared times 2x, x squared times minus 3. Sorry, I've made a silly mistake there, haven't I? I've got an x, I needed a 0x squared plus x minus 10. I need to do this bit, take away this bit, those ones cancel out, and I end up with minus x cubed plus 3x squared. Then I do the first term here divided by the first term here, which is going to give me minus x. This thing I've written up here times by this thing here. So hopefully now you can see that I'm getting the, I'm just doing the same pattern as before. I forgot to bring this x down, didn't I? Minus x times that, minus x cubed, minus x times that is minus 2x squared, minus x times that is plus 3x. This thing take away this thing, those ones cancel out. I get 5x squared, x take away 3x is minus 2x. First term divided by first term gives me, and I'll feel free to fast forward, it's not the most riveting, I'm sure. X squared divided by x squared gives me 5x squared divided by x squared equals 5. 5 times this whole lot is 5x squared plus 10x. 5 times minus 3 is minus 15. Don't forget to bring that 10 down. Then I do this, take away this. Now what I end up with here is minus 12x minus 10 minus minus 15 plus 5. Now at this point I'm trying to do first term divided by first term, and I'm stuck because I've got an x divided by an x squared, and I'm not going to do that because I'm going to go into negative powers of x. So there's my answer, that x to the power of 4 plus x cubed plus 0x squared plus x minus 10 divided by x squared plus 2x minus 3 equals x squared minus x plus 5 with a remainder of minus 12x plus 5. Okay? And then you can write that out as they do in the book as the sort of mixed number, polynomial equivalent of a mixed number at least, minus 12x plus 5 over x squared plus 2x minus 3 is the answer to that divided by that is equal to that whole lot there. So that's how we can do it by polynomial division. And don't forget, if this factorizes, and I'm tantalizing not to tell you where it does or not, even though by now it should be obvious, if this factorizes on the bottom, you can partial fraction this as well, okay? And that takes us right through exercise 1F and in fact 1G as well. I think, in fact, we've finished with chapter 1.